In this video, we're going to be studying chemical changes, which is Unit 4 of the AQA Chemistry specification. Our first lesson is on metal oxides and oxidation versus reduction. Let's begin by recapping the different types of chemical bonding that you should have studied before. The first type of chemical bonding is called ionic bonding. The next is covalent bonding, and the final type of chemical bonding that we examine in GCSE is called metallic bonding. In order to determine whether a substance has one of these types of bonding, you need to know your periodic table. The first thing you need to do whenever you get a periodic table is draw a staircase on it where aluminium is the first element under the stairs, like this. This line will divide the metals versus the non-metals. Those I've shaded in green here are classified as metals, and those that I've shaded in blue are non-metals. It's important to remember that hydrogen, despite being to the left of that staircase, is in fact considered a non-metal at GCSE. The rules for the different type of bonding use the periodic table. If a substance contains both a metal and a non-metal, then it will have ionic bonding. If a substance contains only non-metals, then it will have covalent bonding. Whereas if a substance only has metals, then it will have metallic bonding. Let's apply this to some examples. The first example is iron chloride, Fe for iron, Cl for chlorine. We can see that iron here, found on the periodic table, is a metal. Chlorine, found on the periodic table here, is a non-metal. So therefore iron chloride has ionic bonding because it contains both a metal with a non-metal. Our next example is carbon dioxide. If we find carbon on the periodic table, we can see it's a non-metal. If we find oxygen on the periodic table, we can also see that it's a non-metal. Because this substance only contains non-metals, it must have covalent bonding. Our next example is copper. If we find copper on the periodic table, we can see that it's a metal. And as it's the only element this substance contains, it must be metallic bonding within copper. Your first task is to try to determine the bonding in a range of different substances shown here. You should look at the elements in the formula and decide whether you have a combination of metals with non-metals for ionic bonding, only non-metals for covalent bonding, and just metals for metallic bonding. If you want to pause the video here, attempt these questions and then come back to see the answers. Sodium oxide contains both a metal with a non-metal, therefore it has ionic bonding. Sulfur dioxide contains both a non-metal and a non-metal. So as it contains only non-metals, it must have covalent bonding. Iron contains only a metal, therefore it has metallic bonding. Methane contains non-metals only, so it has covalent bonding. Calcium chloride contains both a metal and a non-metal, therefore it has ionic bonding. And hydrogen chloride contains only non-metals, therefore it has covalent bonding. Now we're going to look at metal oxides. Metal oxides are compounds that contain both a metal and oxygen atoms. For example, magnesium oxide, MgO, sodium oxide, Na2O, and aluminium oxide, Al2O3. And we can describe the formation of these metal oxides from their elements using word equations. To make magnesium oxide, we'd need to react magnesium with oxygen. To make sodium oxide, we'd need to react sodium with oxygen. And to make aluminium oxide, we'd need to react aluminium with oxygen. We can now consider the bonding in metal oxides. As they contain both a metal and a non-metal, oxygen, then metal oxides must have ionic bonding. You may have also noticed that each formula contains a different ratio of the metal to oxygen. For example, in magnesium oxide, there is 1 atom of magnesium for every 1 atom of oxygen. In sodium oxide, there are 2 atoms of sodium for every 1 atom of oxygen. And in aluminium oxide, there are 2 atoms of aluminium for every 3 atoms of oxygen. We can explain why this is the case by describing the process of ionic bonding, which you should already be proficient in. When we describe ionic bonding, the rules we need to remember are as follows. The metal will always lose electrons, and it will lose the number of electrons equivalent to its group number, shown by the numbers at the top of the periodic table here. The non-metal will always gain electrons, and it will gain the number of electrons it takes to get from its group number up to 8. For example, if you were a non-metal in group 6, you would need to gain 2 electrons to get up to 8. If you were a non-metal in group 7, you would only need to gain 1 electron to get up to 8. Let's apply this to the example of the formation of magnesium oxide. If we find magnesium on the periodic table, we can see that it's in group 2. So before it's reacted, magnesium atoms will have 2 electrons in their outer shell. We can show this as follows. You can see here I've drawn X's to represent the electrons in the outer shell of an atom of magnesium. If we now find oxygen on the periodic table, we can see that it's in group 6. Therefore, the outer shell of an atom of oxygen will contain 6 electrons. Now let's apply the rules we just looked at. The metal always needs to lose electrons, and it will lose the number of electrons that is the same as its group number. By losing these electrons, it will reveal a full outer shell beneath. So magnesium needs to lose 2 electrons. Oxygen is a non-metal and needs to gain electrons. As it's in group 6, it needs to gain 2 electrons. So I'm going to show magnesium losing 2 electrons. And we can see that the 2 electrons lost by 1 atom of magnesium are transferred to 1 atom of oxygen. So from oxygen's perspective, it has gained 2 electrons. Now we need to consider what these will form. When you lose electrons, electrons are negatively charged. So if you lose your negatives, you become positively charged. So by losing 2 electrons, magnesium actually becomes an Mg2+ ion. Because it has lost 2 electrons, it has lost 2 negatives. Oxygen has gained 2 electrons, so therefore it has gained 2 negatives. So an oxide ion, the ion of oxygen, will actually have a 2- charge because it's gained 2 negative electrons. We can see that the charges of the ions formed, 2+ and 2-, are equal and opposite. So the charges of the ions will cancel out and the 2 ions will bond together, forming an ionic bond between the metal and the non-metal. We only need 1 ion of magnesium for every 1 ion of oxide to cancel out the charges fully, and therefore we get MgO, where the ratio of magnesium to oxygen is 1:1. Now let's try to describe this process in words, as if it was a 6-mark question on an exam. The first thing that occurred was magnesium lost 2 electrons, but we need to say how many atoms of magnesium there were. This whole representation here shows the outer shell of 1 atom of magnesium. So we can say 1 atom of magnesium loses 2 electrons and forms an Mg2+ ion. Here's the 1 atom of magnesium losing 2 electrons, and here's the Mg2+ ion. We can also say that 1 atom of oxygen, here it is, gains 2 electrons, here they come, to form an O2- ion. Here's the O2- ion. Finally, we need to state that the electrons that magnesium lost were transferred to oxygen, because ionic bonding is all about the transfer of electrons. So we're going to finish up with this sentence here. The 2 electrons that were lost by 1 atom of magnesium this bit here, are transferred to, these arrows, one atom of oxygen, this here. Now let's apply this to another example. Let's look at the example of sodium plus oxygen forming sodium oxide. If we find sodium on the periodic table, we can see that it's a group 1 metal. Therefore, when we draw sodium, we will draw it with 1 electron in its outer shell. When we find oxygen on the periodic table, we can see that it's a group 6 non-metal. So we're going to draw our oxygen with 6 electrons in its outer shell. As a group 1 metal, sodium needs to lose 1 electron in order to complete its outer shell. In other words, revealing a full outer shell beneath. But oxygen needs to gain 2 electrons in order to achieve a full outer shell. And therefore, 1 sodium is not enough because it can only transfer 1 electron. So this oxygen needs another atom of sodium in order to gain 2 electrons. If sodium loses 1 electron, then it will form an Na plus ion. If it's lost 1 negative, it will be 1 plus. But because this has happened twice, we will form 2 Na plus ions. We only had a single atom of oxygen gaining 2 electrons. So therefore, we're going to draw a singular O2- ion. We can see that the charges of the 2 sodium ions, plus and plus, cancel out the 2- of the singular oxide ion. So therefore, when we cancel out the charges, the formula of this product is Na2O, with 2 sodiums and 1 oxygen in this 2:1 ratio. Let's now try to word this. In the first stage, we needed 2 atoms of sodium to each lose 1 electron. This formed 2 Na plus ions. 1 atom of oxygen gained 2 electrons, and this formed a singular O2- ion. Finally, we'll describe the transfer of electrons. The 2 electrons lost by 2 atoms of sodium are transferred to 1 atom of oxygen. Let's now look at our final and most challenging example of aluminium plus oxygen forming aluminium oxide. If we find aluminium on the periodic table, we can see that it's a metal in group 3. So its representation will be aluminium with 3 electrons in its outer shell. Oxygen is in group 6 and therefore has 6 electrons in its outer shell. Aluminium as a metal needs to lose electrons, and it will need to lose 3 in order to reveal a full outer shell beneath. Oxygen, however, as our non-metal, needs to gain electrons, and it needs to gain 2 in order to get a full outer shell. This oxygen can be perfectly satisfied by this aluminium losing 2 electrons, but this aluminium needs to lose 3. So the aluminium would lose its first, its second, and this oxygen would have a full outer shell. But this aluminium would be unable to lose its 3rd electron if it were reacting with only 1 atom of oxygen. So therefore, we're going to need another atom of oxygen. Now, this aluminium can finally lose that 3rd electron, and oxygen can gain it. But you can see that the oxygen needs to gain 2, and in this arrangement, it's only gained 1. So we're going to need another aluminium. Well, this oxygen could gain its 2nd electron from this aluminium here, as so, but this aluminium still has 2 electrons left to lose in order to achieve a full outer shell. So we're going to need another oxygen. Finally, we have an arrangement where this aluminium can lose its final 2 electrons to make the total of 3 lost and 3 lost here, and all oxygens have gained 2 electrons. So, to summarise, we've had to use 2 atoms of aluminium, each losing 3 electrons, and 3 atoms of oxygen, each gaining 2 electrons, in order for both the metals and the non-metals to lose and gain the appropriate number of electrons. Let's draw the ions now that this forms. Each aluminium atom has lost 3 electrons. If it's lost 3 electrons, then it will become 3+ charged as its ion. This has happened twice, so we will form 2 aluminium 3+ ions. We've had 3 atoms of oxygen, each gaining 2 electrons. If you gain 2 negative electrons, you become 2- charged, and this has happened 3 times. So we form 3 O2- ions, 1, 2, and 3. We can see that the number of positive charges in total, 6+, cancels out the number of negative charges in total, 6-. And to achieve this, we needed 2 aluminiums for 3 oxygens. So therefore, we end up with the formula Al2O3 in the 2:3 ratio. Let's now try and word this. To begin with, we had 2 atoms of aluminium, 1 and 2, each losing 3 electrons. This formed 2 Al3+ ions. Next, we had 3 atoms of oxygen, 1, 2, and 3, each gaining 2 electrons. This formed 3 oxide or O2- ions, 1, 2, and 3. We can say that the transfer occurred as follows. The 3 electrons lost by 2 atoms of aluminium, atom 1 losing 3, atom 2 losing 3, are transferred to, the arrows, 3 atoms of oxygen, 1, 2, and 3. Now I want you guys to have a go at task 2 on metal oxides. The first thing you need to do is complete these word equations by filling in the gaps. The second thing you need to do is explain the formation of aluminium oxide as I did in the previous slide. Pause the video here, then come back for the answers. 1a. Sodium plus oxygen should make sodium oxide. 1b. Magnesium plus oxygen should make magnesium oxide. 1c. In order to form aluminium oxide, we need to react aluminium with oxygen. Complete the paragraph explaining the formation of aluminium oxide. 2 atoms of aluminium each lose 3 electrons, forming 2 Al3+ ions. 3 atoms of oxygen each gain 2 electrons, forming 3 O2- ions. The 3 electrons lost by 2 atoms of aluminium are transferred to 3 atoms of oxygen. Now let's try to construct balanced symbol equations for the formation of metal oxides. In our first example, we'll look at the formation of magnesium oxide. We've decided previously that the formation of magnesium oxide results in a formula of MgO, because magnesium lost 2 and oxygen gained 2, so therefore the 1:1 ratio worked perfectly. It's important to write the formula of the product before we start trying to balance the equation, otherwise you'll be balancing for the wrong formula. We need 2 things to react and we need to write their formulae. The important thing you need to know about oxygen is that its elemental formula is not just O, it's O2, or a diatomic molecule, like this. This is how we always have to write the formula of oxygen when it's shown on its own in an equation. Metals always have just their symbol as their formula when they're not in a compound, so magnesium is just Mg. We now need to balance this equation. We're going to count the number of magnesium and oxygen atoms, both in the reactants on the left and in the products on the right. On the left, we can see we have one atom of magnesium. In the products on the right, we can see we also have one atom of magnesium. So at the moment, it appears balanced. If we now look at the oxygen, we can see on the left in the reactants, we have two atoms of oxygen, whereas on the right in the products, we only have one atom of oxygen. Therefore, we're not balanced because the number of oxygens on both sides is not the same. I need to make this one oxygen on the right the same as the two oxygens on the left, but I cannot change the formula of magnesium oxide because that wouldn't work in terms of its ionic bonding. All I can do is add coefficients or balancing numbers in front of the formulae in the equation. In order to turn 1 into 2, I'd need to times it by 2, so I need to multiply this whole substance by 2. That therefore results in 2 times 1 of oxygen, and therefore we have 2 oxygens now. We can see it's now balanced for oxygen. But by putting this 2 in front of this chemical formula, I didn't just multiply the oxygen, I also multiplied the magnesium. So therefore I don't have 1 magnesium on this side anymore, I actually have 2. And we can see that we're now no longer balanced for magnesium on both the left and the right. This number here is now a 1, whereas this side it's a 2. So I'm going to need to multiply the magnesium on this side by 2, and then we have the same number of magnesiums both sides and the same number of atoms of oxygen both sides. This equation is now balanced. Let's now write a balanced equation for the formation of sodium oxide. When we examined the ionic bonding, we decided that the formula of sodium oxide was Na2O, because sodium needed to lose 1 electron, whereas oxygen needed to gain 2. So therefore we needed 2 sodiums to satisfy the oxygen's need to gain 2 electrons. The formula of oxygen that must react is O2, and the formula of a metal is always just its symbol. Let's balance this equation. Counting the sodiums on the left, we have 1 atom, whereas on the right, we have 2 atoms. Counting the oxygens on the left, we have 2 atoms, whereas counting the oxygens on the right, we only have 1 atom. I need to balance for both sodium and oxygen. So oxygen needs to therefore be multiplied by 2 in order to make it the same as this side. So I'm going to put a 2 in front of the formula of sodium oxide, and therefore we have 2 oxygens both sides. But by multiplying the entire formula by 2, I also multiplied the sodiums by 2. So that's 2 times 2 sodiums, so actually I've got 4 sodiums this side now. I've only got 1 this side, so I'm going to need to multiply this by 4. We can now see that we have 4 sodium atoms on both sides and 2 oxygen atoms on both sides, so therefore this equation is balanced. In our final and most challenging example, we'll balance the equation for the formation of aluminium oxide. When we examined the ionic bonding, we decided that the formula of aluminium oxide should be Al2O3. Oxygen has the formula O2, and aluminium as a metal has its symbol as its formula. Counting the aluminiums on the left, we have 1 atom, whereas on the right we have 2 atoms. Counting the oxygens on the left, we have 2 atoms. Counting the oxygens on the right, we have 3 atoms. If we start with the oxygen, there's nothing straightforward that I can multiply 3 by in order to turn it to 2. So, what I'm going to need to do is find a number that both 2 and 3 fit into. 6. What would I need to multiply 3 by in order to turn it into 6? 2. So therefore, I'm going to multiply this whole formula by 2. We can see then we would have 2 times 3 oxygens, which would give 6. We now need to multiply the 2 oxygens on the left, so they also give 6. 2 must be multiplied by 3 in order to give 6. So I'm going to place a 3 here in front of the O2. 3 times 2 is 6. And we can now see that we're balanced for oxygen on both sides. However, introducing this 2 in front of the formula of aluminium oxide also multiplied my aluminium atoms. So therefore I've actually got 2 times 2 aluminiums, and therefore 4 aluminium atoms on the right, whereas there is only 1 on the left. So I need to place a 4 in front of the formula of aluminium, and now we can see we have 4 aluminium atoms on both sides and 6 oxygen atoms on both sides, and this equation is now balanced. Now what I'd like you to do is pause the video and attempt to balance these equations by filling in the gaps. If at any point the gap would be a 1, then you can either leave it blank or you can write a 1 in it. The first equation should have balanced as follows. 4 sodiums with every 1 oxygen forms 2 sodium oxides. 2 magnesiums for 1 oxygen forms 2 magnesium oxides. 4 aluminiums for 3 oxygens forms 2 aluminium oxides. 4 lithiums for every 1 oxygen forms 2 lithium oxides. 2 calciums for 1 oxygen form 2 calcium oxides. And 4 ions for 3 oxygens forms 2 iron oxides. When I say 1 oxygen, I don't mean 1 atom of oxygen, I mean 1 molecule of oxygen, which is technically 2 atoms of oxygen, but that's already shown by the formula here. Finally, we're going to look at the key terms oxidation and reduction. Oxidation is a word used to describe when a substance has gained oxygen. Let's look at an example. When we formed magnesium oxide, we can see at the start of the reaction the magnesium did not have oxygen, whereas at the end we can see that it's gained oxygen as it's formed the compound magnesium oxide. So therefore, we can say that magnesium has been oxidized because it has gained oxygen. Reduction is a word used to describe when a substance has had oxygen removed. This is an equation you haven't seen before, but if we look at the equation, iron oxide plus carbon goes to make iron plus carbon dioxide, we can see from the perspective of iron, it was iron oxide to start with, but now it's just iron. So from the perspective of iron, it has been reduced because it's had its oxygen removed. But you could argue from the perspective of carbon, it's been oxidized because carbon had no oxygen, and now it does have oxygen in the form of carbon dioxide, so the carbon's gained oxygen, so it's been oxidized. It's important to know from what perspective, which substance's perspective, you're looking at these. There's actually 2 different definitions for oxidation and reduction, and it depends entirely on the context we're looking at. We might be asked about oxidation and reduction in terms of oxygen, but we also might be asked about oxidation and reduction in terms of electrons, which you may have come across before. In terms of oxygen, as I've just described, oxidation is the gain of oxygen, and reduction is the removal of oxygen. If we were asked about this in terms of electrons, though, oxidation is the loss of electrons, and reduction is the gain of electrons. Don't worry too much about oxidation and reduction in terms of electrons yet, because we're going to look at those in a future video. Your final task is to describe oxidation and reduction in these questions here. Please read the questions, pause the video, give them a go, and then come back for the answers. 1. Define oxidation in terms of oxygen. Oxidation is the gain of oxygen. 2. Define reduction in terms of oxygen. Reduction is the removal of oxygen. 3. In this equation, which element has been oxidized and why? We can see on the left we have calcium, and on the right we have calcium oxide. So therefore, we can say that calcium has been oxidized as it's gained oxygen. 4. From the perspective of copper, does this equation show oxidation or reduction? Explain why. If we look at the copper on the left-hand side of the equation, it has oxygen bonded to it in the form of copper oxide. Whereas if we look at copper on the right-hand side, or the product of this equation, we can see that it doesn't have oxygen anymore. So we can argue that copper has been reduced as it's had its oxygen removed. If this question instead said from the perspective of carbon, we could argue that carbon was oxidized, because as a reactant, carbon has no oxygen, whereas a product, carbon does have oxygen, so therefore it would have gained oxygen. Thank you very much for watching this video. In the next lesson, we're going to be looking at displacement reactions, the reactivity series, and redox reactions, where just at the end there, I spoke about reduction and oxidation in terms of electrons. We'll look at that a bit more next lesson. Thanks very much for watching. See you next time.